Hi, I'm Dr. Lisa Will, Professor of Physics and Astronomy at San Diego City College and the resident astronomer at the Fleet Science Center in Balboa Park. Welcome to our November Astronomy on Tap San Diego. Thank you very much for joining us, either synchronously or asynchronously. We're glad to have you with us here in the virtual realm. We have Ashley Lemasters, a graduate student from San Diego State University with us tonight, and she'll be giving us a presentation about dark energy and a means to explore it. But before we do that, we're going to talk about some astronomy in the news. And if you ever have any questions during this live stream, please type them in on Facebook Live. I'll be monitoring the chat and I will be able to get the answers to you. All right, so what's been going on in the news? This is a new impact crater on Mars. And what's really amazing is that you see those little whitish splatters around it, which is ice that has actually been kicked up from underneath the surface. This image was taken by the Mars Reconnaissance Orbiter. And what's really amazing about this one is that this was a case where this impact was in part discovered because the Mars InSight lander experienced the Marsquake from the impact. And so this is the first time, like we've seen new impact craters on Mars, but this is the first time that the impact was also sensed seismically. And those icy bits that you see there are actually ice kicked up from underneath the surface of Mars. And what's really interesting is that we actually can see this from above. The Mars Reconnaissance Orbiter took these two images of the same portion of Mars. The one on the left is the before the impact, and the one on the right is the after the impact. And so we are able to see impacts occurring and sense them with NASA InSight's seismometer. The InSight mission is coming to an end soon. The solar panels are getting covered with dust, much like Opportunities did. And so we will not have this seismic capability for much longer on Mars. But it's been really fascinating to study Mars quakes, and in this case, impacts. Now, these images got a lot of press coverage, but it doesn't hurt to talk about them again because they're pretty pictures, and we love the pretty pictures here. This is M16, often referred to as the Eagle Nebula. The image on the left is the Hubble Space Telescope image of this region in visible light. The one on the right is NASA's JWST image looking at this star-forming region in the infrared. And what you immediately notice in the right image, the infrared image, is that you see a lot more stars. And that's because in the infrared, we have the ability to see through the gas and the dust that these stars are forming from and see the stars themselves that are forming inside the stellar nursery. And so that's the major difference between the amount of dots you see in the left-hand image in visible light and the one on the right in infrared light. And so the one on the right got a lot of press coverage. But one of the other infrared cameras on JWST also looked at the Eagle Nebula. And so now this is comparing the two. So now the one that got a lot of press is on the left. And the one that didn't get as much interest is the one on the right. Both of these images are in the infrared, which are longer wavelengths of light than visible light. And so you can't see these with your eye. But what we're seeing here in the right-hand one is you're getting more of the structure of the gas and the dust that these stars are forming from in this stellar nursery. And if you'll notice about, 2/3 of the way up in the right-hand image, the mid-infrared image, you'll see a bright red dot at the end of sort of a pillar. And that is the light from a protostar, a star that is forming out of that gas and dust in that region. Another pretty image from JWST that was released recently. This is also a protostar, a star that is forming an interesting case called L1527. I know, not a terribly interesting name, sorry. And then if you look really closely at basically the middle of this hourglass shape, you'll notice kind of a straight line going across. And behind that straight line is the protostar. And we call these things protostars because they aren't stars yet. They haven't started nuclear fusion in their cores, but they have started to develop a what we call a circumstellar disk of material, or a protostellar disk around them. And that sort of disk is what you're seeing there in that line. And that's the sort of thing that planets and asteroids and comets are made from. And then the hourglass shape in this case is because as these protostars form, they tend to expel some of the gas and dust from them. And that disk doesn't let the material move out in that direction very easily. So we tend to see these outflows above and below the disks. And then one more JWST thing I have to say, this is something that was released just today. Exoplanet atmosphere data. WASP 39b is an exoplanet that actually JWST looked at previously. You might remember over the summer, there were like a handful of images released. That was early science data from JWST. This is that same exoplanet, that they released some preliminary data from them. And what we've been able to get here is the most precise, I should say, the most detailed, sorry, the most detailed atmospheric composition data for a planet that orbits a star other than our own sun. This planet revolves around a star that is up in the constellation Virgo, located about 700 light years from our solar system. And it's like a Saturn-sized planet. It's a gaseous planet, but it orbits closer to its star than Mercury does to our own sun. And one of the things that was particularly interesting about this discovery is that they found sulfur dioxide in the atmosphere. And sulfur dioxide actually is formed through photochemistry occurring in the atmosphere. And so we're actually seeing photochemistry occurring, which is chemical processes that occur due to starlight, or in our case, sunlight, in an atmosphere for the first time, in terms of seeing it happening in an exoplanetary atmosphere. So this is very exciting. And I don't know about any of you, but it was the exoplanet atmosphere stuff that I personally was the most excited for with JWST. And then one last big bit of news that you may have heard about was the launch on late November 15th Pacific time of NASA's Artemis launch system. So this was the first launch of this system, which is going to take us back to the moon. There were no astronauts in this one. This was an uncrewed test flight. And this was my favorite image from the launch. This was posted on Space Florida's Twitter and was taken from the air traffic control tower of the Space Florida launch and landing facility. Now, in case you've been wondering what the Orion spacecraft on the Artemis launch has been doing since it launched, well, it went to the moon. And it's gone to the moon and has been taking images. And so crews of up to 6 astronauts will be able to use this spacecraft for flying to the moon. You might remember the Apollo missions could only have 3 astronauts in them, but here we can actually have 6. And you might see the Earth setting behind the moon in this image from this test flight that is still ongoing. And so that is just some stuff going on in astronomy news that we thought we could get you up to speed with. Now what I'd like to do is turn it over to Ashley.
Awesome. Thank you so much. I didn't hear about the sulfur dioxide thing. That is so cool.
That just came out today, and I'm going to have so much fun talking to my students about it. The big important thing there is that it's photochemistry, just like photosynthesis, right? And so we're actually seeing that sort of chemical reaction happening in an exoplanet atmosphere. And it's sort of like, it's one of those things like, it should happen,
But
but
finally, like, we
seeing
got proof. Like, hello.
exactly. All right. So I will turn it over to you and I will monitor questions. So hopefully, let's have
Awesome.
fun.
All right. Can you see my screen? Awesome. Okay. Sweet. So hello, everybody. My name is Ashley Lemasters, and I'm going to talk to you today about the unknown universe, dark energy, and the Project Het Dex. So to get started, some preliminary background knowledge back in the 1990s. This is what we knew. We knew that, well, we had a good picture of the universe. We were studying light from the distant galaxies. We had everything figured out. We were good. We got this. We noticed the light was shifted towards the red end of the spectrum as the light traveled, and we're like, yeah, that's it'd be like that. That's normal. So a spectra is what we were using to look at these things. This is an example of a spectra. So that top one there is, say, something that's really close to us, really bright, maybe like the sun. And then that bottom image is what has been red shifted. So notice these lines are the same, but they have been shifted to the right into more red regions. So as we were developing more technology, bigger mirrors, we were sending telescopes into space, we started looking at some standard candles. So some stuff that was really far out that we weren't able to detect before. And in particular, we were looking at supernova type 1a. So these are excellent standard candles. And a standard candle is something that you can use to calculate the distance very reliably to something that otherwise you wouldn't be able to get that distance to. So with supernova, and especially type 1a, they have a very, very specific brightness and how long they last, and we know exactly how bright they should be. So if we know how exactly bright they should be, and we know, hey, that's type 1a, we're for sure about that, we can go, you're this dim, you're supposed to be this bright, and a whole bunch of calculations and stuff, and we're able to find out exactly how far away these objects are. So we were checking those out, getting those measurements for distances, and the cool thing about type 1a supernovae is that it's a white dwarf and a companion star. So this is not like the stars that are just really, really big and they explode and blow up. These are a white dwarf, which is basically like the corpse of a dead star, and it's a companion star, but they're very close together, and the white dwarf starts siphoning material off of its companion star, which eventually spells doom for usually both of them. So I have a really cool video that is from NASA that shows what happens when they reach that critical mass. So here we have the companion star. I love this video, it's so cool. We have our tiny little white dwarf, that little thing in the center is the white dwarf. It is pooling mass and just accreting all of that matter until it reaches a critical mass. And then giant explosion, like there is almost nothing left. It's so cool. But these are the things that we were looking for because we knew exactly how bright they were supposed to be. And exactly, we knew, okay, so we're looking for these guys. We know how bright they are. They're really cool. Stuff's exploding. Everyone loves explosions, right? And so,
Everybody loves explosions.
yes. So once we were looking at these things, we kind of ran into some problems. So especially in 1998, with the launch of the Hubble Space Telescope, we were looking at these type 1a supernovae. Now, these aren't type 1a supernovae, these are just the remnants. These are remnants left over from those events, really pretty. But we realized something. The supernovae were too dim. They were way too dim. And in fact, they kept getting dimmer the farther we looked out. And the farther we looked out, that meant that the faster these things were moving away from us. So their distances didn't correlate well at all. And based on their redshift, we can calculate how fast these things are moving. And we realized, well, they're really moving way too fast. And as we got more information, we looked into it, we got more data, the universe was expanding. So not only was the universe expanding, the farther we looked, the faster things were moving, This expansion was accelerating, which was not at all expected. So as we're peering into this cosmos, we're seeing everything is moving away from us, nearly everything. There's one thing that's not, but I can see if maybe the audience knows or someone else knows. I can give the answer to at the end, but nearly everything was moving away from us. The universe was expanding and that expansion was accelerating. This was insane. So this is the picture that we have after this crazy discovery. We have the start, we have Big Bang, lots of inflation. We have the first stars around like 13.3 billion years ago. Stars develop, galaxies, expansion starts accelerating. And then roughly like 3 to 5 billion years ago, all of a sudden that expansion just takes off. It is accelerating and it is still accelerating today. So, oh my gosh, turned astronomy on its head. No one knew what was causing this. Clearly it was happening, but we have no idea why, which is very exciting. So the current picture of our universe. So imagine this little pie graph. I really like pie. I'm excited for like pumpkin pie this Thanksgiving. But this pie graph is everything that's in the universe. Me, you, my cat who's trying to get in. I'm sorry if you can hear him trying to break in. He's like, what are you doing in there? So this little blue portion, this blue slice, that is roughly 4%. That is everything that you can see. That's baryonic matter. That is me, you, stars, galaxies, gas, dust. That is everything that we can see. That is only 4% of everything. The light blue stuff, 21%, is dark matter. We know it's there. We're like, yeah, we got this dark matter. The rest of that green, that 75% is this dark energy. They dubbed this weird thing that is causing this expansion of the universe dark energy. They really didn't know what was causing it. Something had to be there to make this happen, to make all these galaxies run away from us faster and faster. So 75% is stuff we have no idea what it is, how it works. It's just 75%. Okay, so we dubbed this thing dark energy. And as I'm sure everyone knows, astronomers are the absolute best at naming things. So, so dark energy, astronomers are great at that. So is it dark? No. Is it energy? No, maybe not, probably. We have no idea. So not dark, not energy. So what is it? No idea.
Perfect. Perfect.
So it's one of the biggest mysteries of science. We have no idea what it is. We do have some theories though. One of the most prevalent theories is it's a property of space. So it is the vacuum energy of space. There's a theory that there's particles that just pop into existence, but then they immediately annihilate each other. And that annihilation makes a little bit of energy. And that's what's causing the expansion. And people are like, well, that makes sense because that also tells us why it suddenly started increasing so fast, because now galaxies are very spread apart and that vacuum energy can take over. Unfortunately, that's not enough energy to be causing it. It's off by a factor of 10 to the 57, which is 10 followed by 57 zeros. So we're missing a lot. It also could be exotic new particles or fields. We're not sure. We still obviously have lots of physics to learn. Or it could be that our theory of gravity is wrong. Maybe we don't understand how gravity works at such large scales. So we have this giant astronomy problem. How do you study something that doesn't interact with anything? It seems almost impossible. Thankfully, though, we have a trick up our sleeves. One of the most fascinating projects is HECDEX. This is the Hobby-Eberly Telescope Dark Energy Experiment. They are illuminating the darkness. It's an experiment to produce the largest map of the cosmos and uncover the nature of dark energy. So this is what they are setting out to do. They want to understand what is happening. Here we have a beautiful photo of the Hobby-Eberly Telescope. This is a really large telescope. Unlike a lot of other telescopes, this is just taking spectra. So some telescopes you can take like observational data, so like pictures of like galaxies and that kind of thing. But this guy, just spectra, just spectra. So what they are doing is making the largest map of the cosmos yet. They're making a three-dimensional map of over 2.5 million galaxies. So how does this help? They're doing all this cool stuff. They're actually going to track the rate of expansion and how it has changed over the eons. So they're looking back all the way only 400 million years after the Big Bang. It might be 1,000. So don't quote me on that one, but they're looking very, very far back, and they are looking at how these galaxies are redshifted, how fast they are moving, to see how it has changed exactly from then until now. So they actually are currently collecting data, which is super exciting. I worked on this project when I was an undergrad. It was really cool. The data is available to the public. You could go download it and mess with it if you want to. You probably need Python, the coding language. There's also a Dark Energy Explorers. This is a citizen science initiative where if you want, you can go in and help them identify and classify different Lyman alpha emitters. And it will finish in 2024, so really close to wrapping up, and their results are going to be here soon. I am so excited for what they are going to come up with. Thank you all so much. And are there any questions? And here's my sources.
Oh, thank you so much. I always find it
Ooh.
disturbing that so much of the universe we can't see. We have a hard time detecting. It's one of those things that when I have to explain that to students, I always feel like, oh wow, they're seeing right through me right now. I don't have an answer for them. So I am looking for questions over on Facebook Live. So if anybody has any questions, please ask. And let me go back here. So did not realize that Hobby Everly was just spectrographic.
Yeah, so I was going through their site because their site is gorgeous too. I recommend checking it out. But they're like, Hobby Everly is just spectroscopic. And I'm like, that is so cool.
Yeah.
So,
That's in Texas.
yes, it is.
Yeah.
Let me see if I can show, oops.
Oh, no worries.
I have so this, as I can share my screen. There we go. So this is basically, oh my goodness. Nope. There we go. So this is basically what the interface looks like. So this is Virus. So they have a whole bunch of visible integral field replicable units called IFUs. They're all hooked up to spectrographs. And only a few of these are dedicated to HETDEX, the project itself, from what I understand. Others are dedicated to different parts of astronomy. And in total, though, they use 156 spectrographs, which is super cool.
That is really amazing. I see some gratitude that for an interesting presentation. I've seen a sarcastic comment, but a true one about astronomers and the way we name things. And then I see a question about spectroscopy or spectrographs. Like, can you explain
Oh, for sure.
for people in the audience who might not know what that is?
Yeah, absolutely. So let me see. I have some slides here. That is a great question. So a spectrograph is a machine we use to basically split light up into its component parts. So this is a diagram of a spectrograph. We have light coming in through a telescope, and there's a bunch of optic. Oh, go ahead.
I was just going to say the graphic hasn't quite loaded for us.
Oh, geez. Let's see here. Let's resume the share. Is this any better?
Still don't see it just yet. I think maybe it's too big for Zoom.
Could be.
All right.
Well, I'm so sorry about that, folks. Let me.
Oh, now we see it.
Oh, I see. Okay, I
Now
will
I see
leave it
it.
alone. Okay. All right. So that's a great question. Sorry for the technical difficulties. But so a spectrograph is a tool we use to basically split light up into different wavelengths. So light comes in through the aperture. I'm not sure if you can see my mouse. I don't think so. Okay.
Yeah,
So
I
on
can
the
see your
left hand,
mouse.
oh, can you? Okay, awesome. So light comes into this aperture, it is bounced around off of some mirrors, and then it hits something called a diffraction grating, which is basically a piece of material that has, to put it, the easiest way is like it's like has lots of tiny little lines carved into it, and the tiny lines are able to break up that light. It's bounced back again through a mirror, and then it is fed into a detector. So what a spectrum is that light being broken up, and a spectrograph is the tool we use to do that. And a spectrum is really cool because it's not just like a picture like how you take with the camera. When we split up that light, we can tell so many cool things about the light itself, like what elements are there, what like the intensity tells us like how the abundance of certain things. There's so many things that a spectrum can tell us. It's really cool. Great.
Yeah, this great. This is a great graphic to show what's going on there too. Spectra, we saw spectra when we showed the JWST spectra of the exoplanet atmosphere in the news segment. And for me, I love spectra because they allow us to ask so many questions. What's it made out of? Density, magnetic fields, how much of stuff is there, whether or not it's moving towards our way. Spectra's great. It just doesn't get a lot of pretty picture excitement going.
So not as pretty, but the wealth of knowledge is incredible.
Absolutely. So I had a question about the data set. You said that the data is public, or
Yes.
basically that they're publishing the data set. And this is a survey, right? It's a survey of the sky. Are they aiming at any one particular area of the sky, or are they is it sort of an all sky survey looking?
That's an awesome question. The project is focusing on the area of the sky that kind of encompasses like the Big Dipper. So they're focused on that. And I think this field of view, if I remember correctly, is like 2,000 times the size of the full moon, um, which is pretty big. They're getting a lot of data from it. So that's like where they are focusing. I think the data that's out right now is a list of AGNs, which are active galactic nuclei. The rest of the data is not yet released, but that's like the preliminary, like, hey, check out we got the AGNs. So.
And then, I'm looking to see if we have any other questions, but I know I have one more question. Was you mentioned a sort of a public science aspect to this data set. What was that called again?
Yeah, so oh, I want to exit the, oh, that's an example of a spectra. That's a solar spectra. Let me go back. So it's called the Dark Energy Explorers. On their site, it is this really super cool initiative to do citizen science. So the one really cool thing about astronomy is that novices can help us make really amazing discoveries. So if like you would actually be doing like science, and that's called Dark Energy Explorers. If I could find the link, I could drop it in.
Actually, I think I just found it on the Zooniverse site. So if
Yes.
all right, I will put it in the Facebook Live link, and when I post this to YouTube, I'll make sure I post it there too.
Awesome. Sweet.
All right. There we go. Any other questions? Or is there anything else you would want us to know about this particular project? Like, what are you the most excited about? Because the fun thing about these surveys is that, like, sure, they're looking for dark energy, but there's always the possibilities of using that data for other things. So what are you the most interested about? Oops, are you muted?
Uh,
Oh,
can
there,
you hear
now
me?
I can hear you. Now I can hear you.
Okay. I was like, hello? Okay, there we go. So I'm actually really excited to find out about like galactic dynamics and galaxy evolution. I'm a big galaxy person. So I am definitely most excited about uh the kind of data they're gonna get from that. Um, I am excited about exoplanets. I think that's gonna be really cool. I'm not sure if they can do a whole lot with it now that I'm thinking about it, but um I'm really excited to see what kind of galaxy stuff they come up with.
And then there was a callback to your question about the object that might be moving towards us.
Oh my gosh, that's awesome. Yeah, so there is one object that's moving towards us. The Andromeda Galaxy is actually moving towards us. Um, it's the only thing really in the area that is moving towards us. Um, they're actually going to collide. Our galaxy and Andromeda are going to collide in, I think, roughly like 10 billion years. When I give planetarium shows, I like to joke that don't worry, you can take that day off work. Um, but thankfully, I mean, the Earth won't be fine because that's past the sun's life expectancy. But when they do collide, they are going to merge. But believe it or not, even though there's like hundreds of billions of stars in the galaxies, only like a handful will collide because
Yeah.
galaxies are mostly empty space. And I remember that somebody was like, so astronomers are great with acronyms, but they're also terrible with naming things. So the Milky Way, our galaxy, and Andromeda are going to collide. And the consensus kind of levels around what we're going to name this is Milkdromeda.
No, no.
No,
All right. So
there's got to be a better way.
the moral of the story is never let astronomers name things. I think I actually say that during every planetarium show I give, which is never let
Yes.
astronomers name things. I do see in the chat that people are going to live to see that, and I personally would love to see the Andromeda Galaxy get bigger and bigger and bigger in the sky, because a lot of people don't realize that you can actually see the Andromeda Galaxy right now, even though it's 2.5 million light years away.
Which is amazing.
Yeah,
I
but
love Andromeda. It's one of the only things you can see that's not in our Milky Way with the naked eye.
yes, yeah,
I love it.
and living here in San Diego, it's hard to see it unless you get out somewhere nice and dark, like out in Anza Borrego or something like that.
Yeah.
All right, I'm just going to check to see if there's any more questions in the chat. I don't see anything, but I just want to thank you, Ashley, for such a lovely presentation.
Of
Hopefully,
course.
people watching this will be as disturbed as I always am that baryonic or normal matter makes up so little of the universe. I really don't like to think about that too deeply. Uh,
Same. Same.
and hopefully, someday we will figure out what the rest is. Thank you to everyone in our live stream audience for being with us tonight at Astronomy on Tap San Diego.
Thank
Uh,
you.
thank you. We will probably not do one in December, get past the holiday season while all of us are so busy. So we hope that you keep healthy and safe, and see you in the new year back at Astronomy on Tap San Diego, whether we're still virtual or back in person. You'll find out about it here on Facebook, on Twitter, if Twitter's still around, on Instagram.
Honestly.
I know, right? We will keep you posted. And for those of you who are watching on YouTube or on Facebook without us being live, if you're watching us asynchronously, always feel free to leave questions and we'll get to them for you. All right. So thank you very much, everyone. Y'all have a good evening, and hopefully we'll see you back here again soon.